Alright, so today's lesson is number 6, Radioactive Decay, and I have a PowerPoint we're going to go through here. There's still a little bit of math and problem solving in today's lesson, but we're going to do some review of chemistry, and then we're going to look at specifically radiation, radioactive decay. Alright, so quick review of chemistry. So you have an atom. The atom has protons, neutrons, and electrons. We have an atomic number, and that atomic number tells you the number of protons in the nucleus, and I'm going to write that as a capital Z. Then we have the neutron number, which I'll write as a capital N, and just like it sounds, it's the number of neutrons in the nucleus. And finally, the atomic mass, which I'm going to write as A. It is the number of protons and neutrons in the nucleus. So when I write this, X here will be the symbol for an atom. You can use, for example, He for helium if you want. A, okay, that is the atomic number, the number of protons and neutrons. In our case of helium, it would be 4. And Z is the number of protons only in the nucleus. So again, in our case with helium, that would be 2. So if we look at this example, right, so here we have gold 197. So 197 tells you the number of protons and neutrons. 79 tells you the number of protons. Also, 79 tells you what element it would be. So if you did have a periodic table, you can just go look at number 79 and say, oh, it's gold. Right? Alright, so if you wanted to figure out specifically how many neutrons there are, all you have to do is take 197 and subtract 79. So that would be 118. So there'd be 118 neutrons in that atom. Alright, so the mass of all of these particles, we have the proton and neutron. Now their masses aren't quite the same. Even though when we look at the atomic mass in the examples we're doing, we're just adding like 1 for each. They're not exactly 1. Okay? We're rounding them to 1 just for our purposes because we're just counting particles in the nucleus. But their masses are slightly different. Right? The neutron is slightly heavier than the proton, and that's a very important point. The electron, however, is much smaller. Okay? Now, these are in units. We write U. 1 U is called an atomic mass unit, and it's equivalent to 1.66 times 10 to the power of minus 27 kilograms. Or it's exactly 1/12 of the mass of a carbon-12 atom. Okay, if you don't remember this from chemistry, that's okay. That's why we're going over it again. Next, isotopes. So isotopes are when you have a certain element, and that element is defined by how many protons you have. But you could have a different number of neutrons in the nucleus. So let's take a simple one, the simplest one, hydrogen. Hydrogen has 1 proton and 1 electron orbiting. So we would write it as 1 and 1. Because there's 1 proton and a total of 1 proton neutrons. But if I were to throw in another neutron there, it's still considered hydrogen because our elements, the naming of our elements is based on how many protons there are, and there's still 1 proton. But this is called an isotope of hydrogen, and we would call it hydrogen 2, where 2 represents the atomic number. Now this is a special isotope, so we actually call it deuterium. Similarly, if you were to throw another neutron in there, that would be hydrogen 3. This is also special. We name it tritium. Alright, so now let's look at what radiation is. Lots of people hear radiation and they start freaking out. But radiation isn't necessarily dangerous. I mean, there's radiation right now shining in your faces because you're looking at a computer screen. Right? And that's visible light. Right? That's electromagnetic radiation on our visible spectrum. And it's not dangerous. Right? So people tend to confuse radiation with what we call ionizing radiation. Ionizing radiation is the dangerous one. It means the radiation has enough energy to strip those electrons off the atoms, right? Which can disrupt things like DNA. And that's the dangerous ones. A lot of people think microwaves and cell phones emit ionizing radiation, but they do not, right? Ionizing radiation, in terms of electromagnetic radiation, would be high energy electromagnetic radiation, things like UV rays, gamma rays, right? X-rays, right? And your cell phone does not transmit a signal with X-rays, right? It's a signal that's even lower in energy level than visible light. Same with microwaves. Microwaves emit microwaves, right? And they have a huge wavelength compared to visible light and a lot less energy. Okay. Energy is related to frequency. And if you remember from our waves unit, if you have a large wavelength, you have a very small frequency. Okay. So electromagnetic radiation that's ionizing is UV rays. And you should know that because you're probably told all the time in summer to make sure you put on some sort of sunblock when you go outside, because those UV rays are dangerous and you want to protect from them. However, a lot of people do take this a little too far and think that a single X-ray is going to be dangerous. I'll talk more about X-rays later, but another ionizing radiation I want to talk about is particulate radiation. Particulate radiation is what it sounds like, radiation due to particles, right? As opposed to an electromagnetic wave. I think I've already talked about all this. So particles can, say, be shot out of nuclei if you have an unstable nucleus. You can have electrons shot with high energy, or you can have sort of alpha particles, which we call helium nuclei, because it's just a particle with 2 protons and 2 neutrons shot out with high enough energies. Okay, and this can be particulate radiation. So how does that work? Well, we have something called the strong nuclear force. Strong nuclear force is called the strong nuclear force because it's the strongest force we know of. It's 137 times stronger than electromagnetic force. And don't even talk about gravity. Gravity is extremely feeble. Right? But the strong nuclear force, unlike the electromagnetic force, has a limited range. It doesn't act over infinity. And so when you have very, very large nuclei, sometimes they can sort of become unstable and shoot something out. And the strong nuclear force can't bring it back in. It's out of its range. Okay? And that's where particulate radiation comes from. So we're going to talk about 3 types of ionizing radiation. We're going to talk about alpha particles and beta particles, which are particulate radiation, and gamma rays, which are high energy electromagnetic radiation. All right, so let's start with alpha radiation. So when a nuclei has too many protons to be stable, they will often emit a particle that has 2 protons and 2 neutrons, which, like I said before, is the exact same as a helium nuclei, just a helium atom without the electrons orbiting it. Right? These are called alpha particles. And because they have no electrons orbiting it, they have a charge of +2 due to those 2 protons they have in their nuclei. Okay, alpha particles aren't too dangerous. They can travel a few centimeters through air. Right? They cannot penetrate your skin. Right? And you have alpha particles in your house. Right? If you have a fire detector. I'm assuming everyone has a fire detector because it's law for you to have one. And I'm assuming it's working because it's law for you to have it working as well. But they emit, they have a radioactive source inside of it that emits alpha particles. And then they just have a detector that detects to make sure those alpha particles are hitting it. Smoke will actually sort of disrupt or absorb those alpha particles. And your detector is going to go, I'm not detecting the alpha particles anymore. Beep, 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 beep. Right? So there is a lot of use for these things because it has a plastic cover. I mean, alpha particles will only travel a few centimeters, and they don't have a high enough energy to even pass through a piece of paper. So they're not going through that plastic cover at all. So don't start freaking out. You're okay. So if we were to write this, so let's say you have an atom. Some atom, let's call it X, has a certain number of protons and neutrons and a certain number of protons. Because it emits an alpha particle having 2 neutrons and 2 protons, and so we write a 4 up here for its atomic mass, and a 2 for its atomic number. Okay? And because conservation has to apply, the new element we get, we can easily figure out what it is by simply subtracting 2 protons from the previous nucleus and 4 protons/neutrons from the previous nucleus. Alright, so an example would be radon gas. So let's say you have radon. Radon has an atomic number of 86 and an atomic mass of 222. So if we release one of these helium particles, right, alpha particles, helium nuclei alpha particles, right, that's a 4 and a 2. So we're just going to subtract 4 from 222, and that'll give us 218, and we'll subtract 2 from 86, which gives us 84. So how do we know that it's a polarium? Well, we look at a periodic table. Okay, and where is radon? Right there. There's radon, and if we subtract 2 from the atomic number, it becomes 84, and the element that's 84 is right there. So that's where we get that number from. Alright, now, because these are alpha particles, even though I said they're very useful and not so dangerous, they could be dangerous if you ingest them, or if you breathe them in. Because I said they can't penetrate the skin, but if you ingest something that would give off one of these byproducts, or breathe it in, then it could be quite dangerous. So don't do that. Where could you breathe it in from? It's pretty shocking, but if you smoke, you're doing it all the time. Right? Most people who smoke just think it's bad for you because of the chemicals, but it's also bad because there's a lot of radiation in those chemicals. So don't smoke. So let's do an example. We're going to predict the daughter nucleus that results from the alpha decay of radium-226. Okay, so radium-226, we'll go over here. This is a question in our handout. So radium-226, where is radium? It's right there. So radium has an atomic number of 88. So we're going to write this as Ra, and it's 226 with an atomic number of 88. All right, so that's going to give us something new, plus an alpha particle, right, which is 4 and 2, and then plus some energy. So what are we going to get here? Well, we have to conserve all these numbers. So 226 must equal something plus 4. So we can write it as 222. Same with 86. Oh, sorry, 88. I already did the math in my head. Same with 88. It must equal something plus 2. So 86. So what is it? Well, go look up 86, and it's radon. So there is the daughter nuclei, radon. All right, so the next part or type of particulate radiation I'm going to go over is beta radiation. This is when a nuclei has too many neutrons to be stable. So what happens then is one of those neutrons is going to turn into a proton. Yes, that can happen. The weak nuclear force is thankful for that. So charge has to be conserved here. You have a neutron which has no charge, turning into a proton which has a positive charge. So in order to balance the charges, we also get an electron. So now something with no charge gives us something with both a positive and a negative charge, which add to 0. So charge is being conserved. And that electron gets shot out of the nucleus. And that is what a beta particle is. It's a high energy electron. So you can see here, I wrote it as, here's our beta particle. Right? We have 0, it doesn't have any protons and neutrons, but I give it a -1 for its atomic number, because that really looks at charge as opposed to simply just the number of protons. All right, so what happens then is the total number of protons and neutrons stay the same. If you just have a neutron becoming a proton, the total number between them stays the same. However, we get 1 extra proton there. Right? And then something's over here. This is called a neutrino. Well, specifically, the line above it means it's an anti-neutrino. So what are neutrinos? Well, around the 1930s, people were observing beta decay, and they realized energy was not being conserved here. And so to solve this problem, a physicist named Wolfgang Pauli proposed the existence of some neutral particle that's much, much smaller, 1/10,000,000th the mass of an electron, so much smaller than an electron, that is also being emitted simultaneously with that beta particle. And because it's something that is so incredibly small and has no charge, it was very difficult to detect. So it wasn't until 1956 that these neutrinos were successfully detected in the laboratory. So neutrino, that name I believe is Italian. It just means little one. Okay, so that's what neutrinos are. So another thing physicists noticed in the 1930s is that if you had a high enough energy in a small enough space, so a very, very high energy electromagnetic radiation, sometimes it would just disappear. And instead, it would create particles in its place. So this is energy creating mass, and we'll talk about more about that in our next lesson. So energy creating mass. And not just any mass, it created a pair. Right? So we call this pair production. Now the interesting thing about this pair was one was an electron, and one was another particle identical in mass, but with the opposite charge. So they called this the anti-electron, which is now known as the positron. So this is where antimatter comes from. Now, antimatter was originally proposed by Paul Dirac when he first created a theory that combined what we call special relativity and quantum mechanics, which I'll talk more about in grade 12 physics. Right? And his theory predicted all of these other particles, these pair of particles that all matter should have. And then, like I said, it was discovered. And what we have in our example here with beta decay is whenever we have a beta decay, or I should call this a beta net minus decay, where we get an electron shot out of the nucleus, we also get an anti-neutrino shot out from the nucleus. Okay, I'm going to come back to carbon-14 later, but we have other forms of beta decay. So like I said, you could have a neutron change into a proton and emit an electron, but you could also have a proton change into a neutron and emit a positron. Right? Again, charge is being conserved. A proton which has a +1 charge becomes a neutron which has no charge. So to conserve charge, we need another positive charge, and that's the anti-electron, or the positron, that gets shot out of the nucleus. And so I've written it here in this example. This is called a beta plus decay, where we have a positron being emitted. Now, when we emit a electron, we also get an anti-neutrino. Now, there are 3 types of neutrinos. I'll talk about those more in grade 12 physics. But the type of neutrino we get here is called an electron neutrino. So we get an anti-electron neutrino. But when we emit a positron, we get just a normal electron neutrino, not an anti one. And the last type of beta decay is electron capture. This is where the nucleus actually captures an electron, and it'll sort of combine with a proton to create a neutron. So again, a negative and a positive charges combining to form a particle with no charge, our neutron. All right, so part B says we're going to predict the daughter nucleus of beta minus decay for thorium-234. So let's write thorium, so that's TH. 234, and if you want to know the atomic number, you have to find it on here, and it's right there, so 90. All right, so we're going to get, because it's telling us we get beta minus decay, so we're going to get a beta particle, which looks like this, and because we get an electron, we're going to get an anti-neutrino. Writing a line above it just means antiparticle. Okay, so what's going to be here? Well, we know the atomic mass is staying the same. The number of protons and neutrons in the nucleus isn't changing, so that's still 234. But we're getting that extra proton, so that's going to be 91. And that's going to be right here, protactinium, so Pa. Right, so there's our beta decay. All right, so I'm going to go over carbon-14 because carbon-14 is a very famous emitter of beta particles. All right, so it'll become nitrogen 14, and we'll get that beta particle sent out. And the reason why it's so famous is because we use it to predict the age of any organic matter, which I'll talk about shortly. First, now I said alpha particles don't travel very far, just a few centimeters in air. Beta particles have more energy. They travel faster, they can travel farther in air, and they can penetrate skin about 1 centimeter. So they're a little bit more penetrating because they're moving so much faster. However, because alpha particles have more mass, if you were to breathe in some sort of smoke or something that emitted alpha particles, they are more dangerous because they can be more ionizing. Okay, so don't eat your smoke detector. I'd hope that'd be kind of obvious though. Next is gamma radiation. So when we get nuclear decays that release beta particles, often we also get sort of an excess of energy. And that energy is in the form of electromagnetic radiation. So not particulate radiation, but EM radiation, and high energy EM radiation. In this case, gamma rays. And gamma rays are quite dangerous. So I said alpha particles couldn't penetrate paper. Beta particles can, but they can't penetrate aluminum. If you want to stop gamma radiation, you need lead. Okay, and now I said that you don't need to worry about things like X-rays, and the reason why I'm going to talk about now. So if you're exposed to radiation, the internationally recognized unit for measuring a certain radiation dose is called a sievert, SV. Now there is natural background radiation. There's radiation everywhere, right? It's natural in the background. And it's about 3.1 millisieverts per year. So that means you are exposed to natural background radiation of 3.1 millisieverts per year. Now, if you were to get, say, an X-ray scan of your whole body, one scan is 0.00007 millisieverts. Okay, if you were to, say, have a limit of 0.25 millisieverts per year, that means you'd have to get 4,000 X-rays a year. I really hope you're not getting 4,000 X-rays per year. I don't know anybody who is. However, you do have people whose occupation is to work with X-rays, such as dentists. And of course, because they're constantly using them, they usually, as you notice, leave the room and have like protection or things like that. Right? So last thing I'm going to talk about then is half-life. So if you have a particle that's going to radioactive decay, it is not possible to determine when it will radioactively decay. Can't do it. However, if you have 100 particles that will radioactively decay, we can determine when half of them will decay. So this is called half-life. And we can use half-life to actually date objects. Right? Archaeologists, geologists will use radioactive dating for different radioactive elements to date objects. Now, if you wanted to date organic objects, one of the easiest one is carbon dating. Right? The carbon-14 that I just recently talked about. So what happens is there's carbon dioxide in the air. A certain percentage of that carbon in the carbon dioxide is carbon-14. It's radioactive. And we constantly breathe it in and breathe it out. Plants will breathe it in and store it. And then animals will eat those plants. And then other animals will eat those animals that ate those plants. So there's a certain amount of radioactive carbon in every living thing. However, when you die, you stop eating. And so you stop taking in this radioactive carbon. And over time, the radioactive carbon inside of you will decay, and the amount that is left will tell people how old it is, knowing the half-life of that carbon-14. Okay, so half-life works like this. If you had 100 particles, after it goes to half, right, a certain time has passed. Once that 50 particles goes down to 25, the exact same amount of time has passed. Once that 25 has gone down to 12 and a half, the exact same amount of time has passed. Okay, so that's how half-life works. And we have an equation that we can use. It's on our handout here. So here we have A, the amount of radioactive material equals the initial sample, how much you had initially, times a half to the power of T, the time that has passed, divided by H, the half-life of the object. So let's do a little sample problem here. Here we have aluminum 30. It has a half-life of 3.6 seconds. Okay, it's a very short half-life. What percentage of an initial sample will remain after 10 seconds? So we have our equation. A equals A naught times 1/2 to the power of T over H. Since we want to know the percent of the initial sample, we just divide by A naught. So we have A over A naught, right, which is how much we have now compared to, divided by how much we started with, equals 1/2 times the power of T, which is the time that has passed, which is 10 seconds, divided by H, the half-life, 3.6. And if we put that on our calculator, we get 0.146, or changing that to a percentage, 14.6%.